Hello everyone, good evening. Okay, so welcome to our third lecture. Okay, so I think we have about 20 of you here, and probably the rest will join in along the way. All right, so next week is of course Chinese New Year week. All right, so there are no classes. Okay, so after today, I will see you all again the week after next, that will be in February. Okay, so just take note of that. So for today, the plan is basically we will just review a few slides from the last chapter, okay, which I asked you to have a look at it and try. Okay, so I'm not sure how many of you have tried it. Okay, but we'll just review those slides just to make sure you understand how those concepts work. And then we will go on to the tutorial. Okay, we'll go on to the tutorial. Tutorial 1. So in tutorial 1, we have some questions on the number systems and programming. Okay, and after that, we will go on to the lecture 5, which is on more MIPS programming. Okay, so I think we'll get started. All right, and the rest will probably be joining in along the way. Okay, can everybody see my screen over here? Okay, thank you. Okay, so there were a few slides that I sort of just showed you and asked you to try and figure out for yourself how it works. So I hope you have thought about it. Okay, so if you recall our MIPS processor, okay, last lesson we went through quite a few instructions. Okay, the basic R-type instruction, which is with addition of 2 registers and putting the result in another register. Then we also talked about this add I, which is adding an immediate value. Okay, so right now, if you look at all this and it looks like some Korean language, okay, that means you have sort of forgotten. All right, then you need to sort of recap. Okay, as I mentioned, the whole of MIPS is all linked together. Okay, so everything is progressive. Okay, so if you forget or you have not sort of caught up with what we covered in 1 week, then the following week we're going to learn new instructions, new programming techniques, and then you will still be a bit lost. Okay, so you need to make sure you sort of keep up at least some general idea of what is happening, then you'll be able to follow a bit more easily. Okay, so we are looking at all these different operations and sort of understanding how it works. Okay, and one of the things that we also talked about was that the MIPS doesn't necessarily implement all the functions. All right, and some functions can actually be achieved by some other approach. Okay, so one of the things we talked about was this NOT operation. So basically we know that NOT operation is to flip the bits. Okay, 1 becomes 0, 0 becomes 1. Okay, but there is no explicit NOT instruction in the MIPS. Okay, so we do not have this. Okay, but we can actually achieve this operation, I mean the same objective, by doing a NOR with a 0. Okay, so how does this work? Okay, so let me give you an example. Okay, so let's assume that you have this data. Okay, so I'm going to just give a 8-bit data. Okay, so what we're going to do is we're going to implement the NOT function using the NOR operation. Okay, so let's assume that I have a register T0 and the T0 has a value of 1011 0011. Okay, and I'm going to do a NOR operation, okay, with the 0 register. Okay, so if you the 0 register is basically a register where all the bits are zeros. That means all the bits here are 0. Okay, so of course MIPS is 32-bit. Okay, but just to make it simple here, I'm just looking at only 8 bits. All right, so if I do this, okay, now what is the non-truth table? So let's just put the non-truth table here so that everybody is clear. Okay, so for the non-truth table, 0 0 0 1 1 0 1 1. Okay, so it's basically the opposite of OR. Okay, so for OR, as long as any input is 1, the output is a 1. Okay, when all inputs are 0, the output is a 0. So for NOR, it's the other way around. So this would be a 1 and this tree would be a 0. So this is the NOR gate truth table. Okay, it's the opposite of the OR gate. So with this, let's go ahead to evaluate this. All right, so if I look at the outcome 1, okay, so we start with LSB for example, 1 OR with 0 will give me a 0. 1 OR with 0 will give me a 0. 0 and 0 will give me a 1. 0 0 will give me a 1. 1 OR with 0 will give me a 0. 1 OR with 0 will give me a 0. 0 and 0 will give me a 1. And 1 and 0 will give me a 0. Okay, so that is the outcome we will get, okay, based on this truth table here. Okay, and now if I look at this and this, what do you see? It is equivalent to doing a NOT operation. Okay, because you can see that all the bits have flipped. Okay, the 1 has become a 0. Okay, the 0 has become a 1, and so on. Okay, so that is basically how we can leverage, okay, what we already have to do something that we want. Okay, and this is quite a common thing in hardware design. All right, in hardware, basically it all comes down to the economics of it. All right, you want to maximize the features and functionality with as minimum hardware as possible. All right, and to do that, you try to think of creative ways of solving the same thing using what you already have. Okay, so this is one example of how that works. Okay, that means you can do a NOT operation without having an explicit NOT instruction. Okay, you do it with a NOR with a 0. Okay, so if you look back at the slides, there was actually another example here in the next page where we say we can also get a NOT operation if I do an XOR with 1. If I do an exclusive OR with 1. Okay, so how does that work? So let's do the same thing. Okay, over here. Now I'm going to put the XOR truth table here. Okay, so for exclusive OR, the rule is simple. As long as both the inputs are different, then the output is a 1. If the both inputs are the same, the output is a 0. Okay, different inputs, output is a 1. Same inputs, output is a 0. Okay, so that is basically the XOR gate. Okay, and just now the slide said that if I do an exclusive OR with a 1, I get the same result. I can do a flipping of the bits. So let's verify that. So T0, okay, I'm going to put the same value 1 0 1 1 0 0 1 1. Okay, and then I'm going to do with a 1. So let's assume that one of the registers, let's say T2, already has all 1s inside. So I'm just going to do a exclusive OR in this case with all 1s. Okay, so what will be the result? Okay, so the rule is simple. As long as the inputs are the same, the output is a 0. When the inputs are different, the output is a 1. Okay, so again, you can see that this and this is basically you're doing a NOT operation. Okay, where 1 becomes zeros and all the zeros become 1s. Okay, so again, this sort of shows you how to perform operations, different operations using what we already have. Okay, so that is the idea behind these two slides. Okay, yeah, and so that was this. And the last slide that I have not gone through is this, which is load upper immediate. Okay, and OR. Okay, so in this slide, okay, basically the question is, how do I load a 32-bit constant into a register? Okay, now, so this is an interesting thing. Okay, so the actual instruction decoding and the format, we haven't sort of looked at it yet. Okay, but basically the thing that we have to understand is all our registers are 32-bit. Okay, all our registers are 32-bit. Now, that means it also means that all the instructions we execute, okay, any instruction that we execute is also 32-bit. Okay, it's also 32-bit. All right. So out of the 32 bits, okay, we need to definitely set aside some bits to tell the processor what is the instruction I'm executing. Correct. Okay, at the bare minimum, I need a few bits to specify the operation I am trying to carry out. All right, which means that out of the 32 bits, out of the 32 bits that I have, okay, I need to set aside something, some bits to tell the processor what is the operation. So that is basically what we call the opcode. Okay, we will look into this more in the next few lectures. But basically, we definitely need some number of bits to tell the processor the operation we want to carry out, which means that what is left is always going to be lesser than 32. Okay, the number of bits left, okay, is always going to be lesser than 32. Okay, and how can I go about trying to load a 32-bit value into a register? Okay, so example, this is my 32-bit value here. Okay, how do I write an instruction that tells the processor that, hey, I want to take this 32-bit value and put it into my register T0. Okay, because any instruction that I want to specify, since I already set aside some bits for the opcode, I will never be able to fully specify all the bits over here. So that is the constraint we have. Okay, now in order to solve this, you have to break up your operation into two steps. All right, so the first step is basically what we call the load upper immediate. Okay, when we say load upper immediate, what happens is you are only loading the upper 16 bits. All right, so if I look at this instruction over here, LUI T0 with the value AAAA, what happens is the upper 16 bits of the register T0 is filled with this new value AAAA. Okay, and the lower 16 bits are filled with zeros. Okay, the lower order bits are filled with zeros. Okay, so that is the first step. That means I need to load it in two halves. The first, the upper 16 bit and the lower 16 bit. All right, so the first instruction, load upper immediate, takes the value that is specified here and puts it into the upper 16 bits of the register. Now, after I do this, so after I do the LUI instruction, this is what I get. Okay, upper 16 bits with the value, okay, and the lower 16 bits with 0. Then what is the next instruction I must do? The next instruction I must do is what we call the OR immediate. Okay, so this OR immediate is the value that I want for the lower 16 bits. Okay, the lower 16 bits. All right, so how does this work? If you look at this instruction OR immediate with the lower 16 bits, so this lower 16 bits are the value that I want. Okay, and since I specify lower 16 bits only, the upper 16 bits will be 0. Okay, now the OR operation, if you recall, if I do a OR with a 0, there is no change to the original value. Okay, so if I do an OR operation, what will I get as a result? Okay, you can see that 1 OR with 0 will give me 1. 0 OR with 0 will give me 0. So the upper 16 bits will not change. Okay, the original value will be read. For the lower 16 bits, it's also the same thing. Since the lower 16 bits have now the updated value in the new instruction, and in the earlier operation, they are filled with zeros, the outcome will be the values that I specified in this new instruction. Okay, so 0 and 0 will be 0, 0 and 1 will be 1, and so on. Okay, so you can see that this final outcome is actually the full 32-bit value that you originally wanted over here. Okay, the full 32-bit value. Only thing is, you need to split it up into two separate instructions, upper 16 bits and lower 16 bits. Okay, then only it works. All right. So again, this is when you write it at the higher C level, okay, C programming, definitely all of this is transparent to us. Okay, but when you compile and you have these instructions to carry out, then the compiler will do all this in the background for us. Okay, so that is again showing you how the processor makes full use of the instruction set to sort of make sure whatever that you want to do in software, it can still carry it out. Okay, but it sort of breaks it up into maybe a few different instructions to fulfill that objective.
Sorry, Prof.
Yeah.
For the previous slide, right? You said that the opcode means that the register will never be it will always be smaller than 32-bit.
Okay, the register is 32-bit, but you will always have to set aside a few bits for the opcode. So what is remaining will always be lesser than 32.
Oh, okay. So this question is not asking how we can like ignore the opcode. It's more of like, oh, okay.
So we are still limited by the restriction that every instruction will always have some bits for the opcode, and the remaining bits are what we have to deal with. Okay, but since we want to put a 32-bit value, it is never possible because we need to always set aside some bits for the opcode. So that is why you need to sort of break up the objective into two separate steps to fulfill the requirement of loading a 32-bit value into a register.
Oh, so that means in order to do this LUI and OI, we will need two registers.
So you need two steps. The two steps are this is the first step.
Mm-hmm.
And this is the second step.
Okay, then it's possible to do it within one register.
Yes. So it's still the same register, T0 in this case. It's just that you have to break it up into two separate steps.
Okay, thank you, Prof.
The first step is the upper 16-bit. The second step is the lower 16 bits. Okay, so that is basically again showing you how the processor does it. Okay, at the lower level when you have to deal with a 32-bit value to be loaded to a register. Okay, so the MIPS basic instruction checklist. Okay, so in the Luminous there is already uploaded. Okay, the MIPS instruction set. Okay, data sheet. All right, so later I'll go through that. Okay, but this sort of shows you just a summary of some of the instructions that we have seen. Okay, in this set of slides. Okay, so let's move on to the tutorial questions. Okay, so I hope you had a chance to look at the questions. All right, so like I said, even if you don't have time to work on them, at least you have a look. Okay, I think it's good so that at least you have an idea of what we are trying to do in the questions. Okay, so let's go to the tutorial first. Okay, so I think by the time you finish the tutorial, it would be just nice to we go for a break, and then when we come back, we can start the next chapter. Okay, so in the first question here, we are asked to do this subtraction. Okay, and we are told that the numbers are represented in one's complement. Okay, so let's go ahead to do this. Now, the first thing that you want to do is we want to write the binary one on top of the other, with them aligned. Okay, when I say aligned, I mean basically what we want to do is we want to make sure that decimal point is aligned so that we can do what we call the padding of the bits in front and after. All right, to make sure that they are both having the same number of bits. Okay, just give me a minute here. Okay, so let's write it out. So the first number is 0101.11. Okay, and we are subtracting the second number. Okay, so instead of writing it from the left, usually the easier approach, okay, is to follow the decimal point. So the decimal point is here, So we know this 0, 1 and 0, 1. All right, and here is 0, 1, 0. Okay, and then what we can do is we can do what we call the padding. Okay, so to pad, basically you extend the most significant bit and the least significant bit. Okay, so for the least significant bit, you just add zeros. Okay, for the most significant bit, all right, you just add on based on the most significant bit value. All right, so in this case, for example, I just add zeros here and I add one more zero here. So now what you have is you have two numbers, all right, and the decimal point here is aligned. Okay, and now you can go ahead to do the subtraction. Now, if you recall, when we said subtraction, okay, subtraction is actually what? It's actually the addition of the complement. Okay, this is the ones complement in this question here. All right, so what we need to do is, when we say that the first number is subtracting the second number, it is equivalent to saying that we add with the ones complement of the second number. All right, so this has to go through what we call the ones complement. All right, so let's do that first, okay, to understand how that will look like. All right, so I'll do that separately over here. So 0, 0, 1, 0 dot 0, 1, 0, 1. Okay, so I'm going to go through the ones complement. So the ones complement I'll have flip. Okay, so let's do the ones complement. So I do the ones complement, what I will get is this will be 0, 1, 0, 1, 1, 0, 1, 1. Okay, so this is basically the ones complement, which is equivalent to the negative of the original number. Okay, so this is what we are doing now. We are creating the negative equivalent of the number. All right, so once we have the negative equivalent of the number, then we can do the addition operation. All right, so now let's rewrite the first and second number. So the first number is this 0, 1, 0, 1 dot 1, 1, 0, 0. And the second number is actually this number over here, which is the negative version 1, 1, 0, 1 dot 1, 0, 1, 0. Okay, so now that we have the original number add with the complement of the second number, we can go about performing the addition as how we normally do. All right, so let's go ahead and do the addition. So 0 plus 0 is 0, 0 plus 1 is 1, 1 and 0 is 1, 1 and 1 is 0 carry 1. Okay, 1, 1, 1 is 1 carry 1, 1 and 0 is 1, 1 and 1 is 0 carry 1, 1 and 1 is 0 carry 1. Okay, so when you do ones complement addition and you have a carry, okay, from the most significant bit, you need to add it again to the least significant bit. Okay, so the final answer here will be, you still have one more one here. The rest of it will remain unchanged. Okay, so that is your final answer here. 0011.0111. All right, now let's see whether this answer makes sense. Okay, and to understand whether it makes sense, we can look at the actual values. All right, so let's look at the actual values. So 0011. Okay, so let me put it here. 0011.0111. Okay, so in terms of converting binary to decimal, this we know is 3. Okay, because the whole number part is very easy. The decimal point, again, if you are not sure yet, just remember is 2 to the power of -1, 2 to the power of -2, and so on. So this is considered 0.5, which is not 0, correct? So it's not there. 0.25, okay, 0.125, 0.0625, and so on. So you just keep dividing by 2. All right. So this, since 0.5 is not there, so this 3 add together will give me 0.4375. Okay, that means this value here is equivalent to 3.4375. Okay, now if you look at the first two numbers, what will you get? This is 5 and this will give me 75. So it is 5.75 and this will give me 2. Okay, and this will give me 0.3125. Okay, so this will be minus 2.3125. So if you do this, you'll get the answer as 3.4375. Okay, so you can sort of confirm that the binary subtraction you did is actually correct. All right, so that is how you go about doing this question here. Okay, so there's a question here on the one. Okay, so when you do the addition, okay, if you have a carry out, okay, if it is one's complement, okay, if you're dealing with one's complement, you need to bring the carry back to the last bit, the least significant bit, and add it again. Okay, but if it is two's complement, you can ignore the carry bit. Okay, so that is the sort of rule for the carry. Okay, for one's complement, you need to add it back again. Okay, but two's complement, you can just ignore it. All right, so that is why for one's complement, you need to add this one back here to get the final answer. Okay, so that is the approach. Okay, and you get this final answer over here. All right, and we can also sort of verify that the answer is correct. Okay, when we do the conversion from the binary to the decimal, and we can relate it. Okay, and we see that the answer is correct. Okay, so there's a question for more practice. Okay, so I will try to see what resources I can recommend. Okay, if you want more practice to look at all this. Okay, now let's look at the second question. Okay, so a bit similar, all right, but quite interesting as well. So we're going to do the same thing. Okay, we're going to first write out the numbers and we're going to align them, all right, based on a decimal point. Okay, so what you have is 0, 1, 0, 1, 1, 1 dot 1, 0, 1. So that's the first number. Okay, and then the second number I'm going to put here 1, 1. Okay, so I'm going to write it the other way. 1, 0, 1, 0, 1, 1, 1, 0. Okay, so now we can do the padding to make sure that they are both aligned. So here and here. All right, so we are again the same thinking applies. We are taking the first number, subtracting the second number. So the subtraction operation is always equivalent to the addition of the complement. Okay, is the addition of the complement is the equivalent to the subtraction. So we need to take the second number and perform the complement. Okay, so let's do that here. All right, so I have 0, 1, 1, 1, 0, 1, 0 dot 1, 1, 0. Okay, I'm going to do the complement. So I do the complement, what do I get? I click. So 1, 0 dot 1, 0, 0, 0, 0, 1. Okay, so this is basically the negative version of the second number. Okay, because I've done the ones complement. So once you do the ones complement already, now you can go ahead and treat it as a simple addition operation. Okay, so let's do that. So I'm going to write the first number again, 0, 0, 1, 0, 1, 1, 1 dot 1, 0, 1. Okay, and this is the ones complement, number 1, 0, 0, 0, 1, 0, 1 dot 0, 0, 1. Okay, so let's go ahead and do this addition. So now we are basically doing a addition operation. Okay, so 1 and 1 will give me 0, carry 1. This will be 1, 1. 1 and 1 is 0, carry 1. 1 and 1 is 0, carry 1. This will be 1, carry 1. 1, 1, 0, and 1. Okay, now this is the interesting part over here. Now the final answer here is having the most significant bit as 1. Okay, whenever the value is such that the most significant bit is 1, if you remember in the last week's lecture, I mentioned that you cannot treat it, you cannot interpret it as how you would interpret it using your calculator. So I cannot key in 101110 in my calculator and say that is the answer for the whole number part or integer part of this. Okay, because the most significant bit is 1. When the most significant bit is 0, okay, that means the final answer here, most significant bit is 0, then no problem. Okay, you can just treat it as it is and just decode the answer and get the value. But when the most significant bit of the answer is 1, okay, that means this is actually the negative representation. That means the ones complement representation of the final answer. Okay, so whenever you see this, that means to know the actual value, I need to perform the ones complement again. Okay, I need to perform the ones complement again to know the actual value. All right, again, this is only you need to do if the final answer has the most significant bit 1. Okay, so let's go ahead and do the ones complement again. So I need to do the ones complement. So I'll get 1, 0, 0 dot 1, 1, 0, 0, 0, 1, 0. Okay, so I've done the ones complement and I get this. All right, so this now you can decode it as a how you treat the whole number and the decimal part. So this part over here, the whole number part, okay, you will get it as 35. Okay, you key in your calculator, and this part over here will be 0.125. All right, and the only thing is, since the most significant bit here is a 1, that implies that the answer is actually negative. Okay, so that is actually the final answer over here. All right, you can always confirm this again by coming back to the original number here. If you look back at the original number over here, okay, if you key in your calculator, this part over here will give you 23. Okay, give you 23. This part over here will give me 0.625, and this whole number part will give me 58, and this part will give me 0.75. Okay, so that part I believe you know how to do. So if you calculate 23.625, subtract 58.75, you'll get this answer, negative 35.125. Okay, so you just have to remember always that whenever the result has a more significant bit of 1, that means it is actually in the complement representation. All right, so you need to do the complement one more time to know the actual value and then put a negative sign in front of it. All right, that is how you represent the final answer. Okay, if the most significant bit is 0, then it's fine. Okay, you can just take it as it is. Okay, so that is why this question is again a bit different from the earlier one, because the answer is actually negative. All right, So if you have not tried the question yet, all right, then again, you just go through, okay, when you're free, and then you just follow through step by step, okay, and look back at the video again to sort of see how it works, okay. Yeah, so if no questions, I will proceed. Okay, so if you have questions, you can feel free to either ask or put in the chat. Okay. Let me move on this. Okay, so the second question here is on the IEEE 754 format. Okay, so you're asking us how do you represent this decimal value in the IEEE 754 format. Okay, so let's go ahead and do it. So the steps are actually the same as what we discussed for the lecture slides. All right, so the first thing is negative 0.078125. Okay, so if you recall the final answer, okay, for the representation has 3 parts to it. Okay, one is the sign bit. Okay, then there is the 8-bit exponent. Okay, and then the rest is the mantissa. Okay, so the first thing we can immediately say is, since the sign bit is negative, I mean the value is negative, the sign bit is going to be a 1. All right, so that is the first thing we can straight away say. Okay, so the next thing is we need to represent the number in the binary form. Okay, we need to represent the number in the binary form. So in this case, again, the whole number part is always easy. Okay, you can just directly do it in a calculator. Okay, but in this case, the whole number is 0. So the only thing left is the fractional part. Okay, so in terms of the fractional part, okay, to represent it, you have to do continuous multiplication by 2. Okay, so the technique is actually shown in the slides. Okay, so I'll just show it over here again. So you start off with the first number 0.078125, and you multiply by 2, you get 0.15625. Okay, so that will give me a value of, okay, so you need to look at the value before a decimal point. So 0, so this would be the most significant bit. All right, then you do that again. Okay, so this is the same thing is in your lecture slides. So the whole number part, you do continuous divide by 2. Fractional part, you do continuous multiply by 2. Okay, yeah, you can use any calculator you have for the exam. Okay, so if your calculator is able to do this, then you can just use your calculator. Okay, 0.3125 0. Okay, so I'll just go through all the steps so that you understand the process. 0.625, so again 0, and then 0.625 times 2, you get 1.25. So whenever you have a 1, you write the 1, but you discard the 1 for the next step. Okay, so 0.5. Okay, 0.5 times 2 equals to 1.0. So once you hit 1.0, that's the end. It is the least significant bit. Okay, so after I convert this to decimal, okay, the answer is going to be 0.000101. Okay, so this is of course in base 2. Okay, in decimal. Okay, so I'm not going to put the negative, all right, because we already know the negative is representing the sign bit, which we already have updated here. Okay, so that is the sort of first step you can do. Okay, you convert it to decimal. Okay, and at the same time you also can update the sign bit. Okay, so those are the first 2 steps. All right, the next step is normalize. So if you remember, normalize means you move the decimal point, okay, until you have such that a single one and then everything else after that. Okay, that is what you mean by normalize. So you move the decimal point, okay, till you only have a single one, okay, to the left of the decimal point and everything else is to the right of it. Okay, so in this case, we need to move the decimal point 1, 2, 3, 4. 4 places to the right. All right, so that means the value will be 1.01 times 2 to the power of minus 4. Okay, since I moved it to the right, it is a negative 4. Okay, so it's the same maths rule. Okay, that we use in base 10. Okay, but it's now in base 2. That's the only difference. Okay, so this is the normalized value. Okay, you normalize the representation. After you normalize, it's almost done already. Okay, it's only 2 steps left. One is the exponent, the other is the mantissa. The exponent, you look at the power. Okay, and the rule basically says is 127 plus whatever is the power will be your exponent. Okay, the reason why it's 127 is again coming back to the way in which the format is designed. All right, so it is I mean, to understand why it is specifically 127 is you need to go into all the mathematical details of how the format was designed. All right, but for now, I think you can just take it is 127 plus whatever is the exponent value. All right, so this will give me 1, 2, 3. Okay, and then you represent it in binary. So 1, 2, 3 in binary is 0, 1, 1, 1, 1, 0, 1, 1. Okay, and the last part is the mantissa, and the mantissa is basically whatever is left after the decimal point. Okay, whatever is left after the decimal point. So in this case, you only have 2 bits left. So it's 0, 1, and everything else is 0. Okay, all the way until the last bit. All right. So of course, in most cases, we want to represent the answer in hexadecimal to make it easier to be readable. Okay, so to convert a binary to hexadecimal, you just need to group them in bits of 4. So 1011 is one group, 1101 is another group, 1010 is another group. Okay, and then the rest is all zeros. Okay, so 1011 is B. Okay, 1101 is D. 1010 is A, and the rest are all zeros. So you have another 4 more zeros here. Okay, so this is in your base 16. Okay, so that is basically the final answer over here. Okay, so that is how you represent this value, okay, in the IEEE 754 format. Okay, so the steps are exactly the same as what we saw in the lecture slides. Okay, so first you take note of the sign. All right, then you convert the decimal representation to binary representation. Then you normalize it. Once you normalize it, you extract out the power to solve the exponent, and whatever is after the decimal point is the mantissa. Okay, and then you have your final answer over here. Okay, so I think it's quite straightforward. It's just step by step. So as long as you follow the steps, you should always be able to derive or arrive at the final answer here. Okay, so I'll go on to the next question here. How do I get B? B is the first 4 bits, 1011. Then 1011 is B. 1101 is D, and so on. Okay, you convert the 4 bit to hexadecimal. Every 4 bit to 1 hexadecimal. Okay, so let's look at this question. So this one is just to recap some basic C programming practice, I would say. Okay, so we have this partial C program where we want to write the code to do two things. First is read an array into a bunch of integers. To get the user to input some numbers, which will update an array of integers. Okay, at most 10 elements. And after that, you want to reverse the array. Okay, so in reversing the array, we are asked to also provide two versions. One is what you call the iterative version. The other is the recursive version. Okay, so let's do the first part, which is reading the array. So to read the array, I think is really quite straightforward. Okay, so I'm not going to go too much into the syntax and everything. Okay, but I think most of you should be able to do this quite easily. All right, so okay, so you can declare some variable, integer, input. Okay, then of course you normally have a printf statement to say, okay, enter the number. Okay, and then you want to declare again this for the loop count, and then you do a scanf. Okay, so that part all I will not bother. Okay, and I think the main thing here is how do you write the loop. So in this case, you want to capture at most 10 elements. All right, so while the input I, so in this case, we're just saying that the input has to be positive. All right. Okay, and I is less than, sorry, this is the input. Let me rewrite this. And I less than 10. Okay, so I'm specifying two conditions here. One is it has to be positive. Okay, and the other one is that the I is less than 10. Okay, yeah, so the answers I will upload to Luminous, okay, after the lesson. All right, and then you can take the value and put it into the array. So array I is equals to input and I plus plus and so on. Okay, so you have a loop, so this loop will run for 10 iterations. Okay, as long as the input is positive. All right, so again, this is just a simple loop. Okay, now let's look at the reversal. Okay, so to do the reversal, you are asked to explore two options. Okay, one is the iterative, the other is the recursive. Okay, so to do iterative, I think it's quite easy. So basically what you have is you have an array, correct? Okay, and what you want to do is you want to swap. So I want to take this element, swap with this element. All right, this element, swap with this element, and so on. All right, so that is the whole idea. That means the reversal is basically swapping from the two ends and then the next two and the next two and so on. Okay, so let's see how we can write a simple reverse function. All right, so one easy way is you can create two pointers. Okay, where you say one is left and this is right. Okay, so inside here what you can say is the left is going to point to index 0 and the right is going to point to size -1. All right, so the size -1 is basically the last element. All right, and whenever you do swap, you usually have to have another variable called temp. Okay, so that is quite standard. So you declare this three variable and then you basically do a loop to say while the left is smaller than the right, then I do the swap. So the swap, I think everybody knows how to do it, right? You move into the temp. Okay, then the left the right goes into the left, and finally the temp goes to the right. Okay, so this technique I think everybody knows how to do. Okay, swapping with the additional variable. Okay, of course, now after you swap, you have to adjust the pointer. Okay, so over here you can see that once I do the swap, I must make this left increment by 1 and this right decrement by 1. Okay, so I need to adjust my 2 pointers. So I can say left plus plus and right minus minus. Okay, so this is one way in which you can write this function, okay, to do a reversal, okay, iteratively within that same function. Now the same thing can also be of course done recursively. Okay, so a recursive function is in some cases recursive functions can be very elegant, okay, in a sense that you can solve it very in just a few lines of code, okay, but again it is also very dangerous because of the handling of the exit condition. So you will always make sure that the exit condition, that means the point where you stop the recursion, is very clearly defined, okay, and you don't have any case where something can go wrong. Okay, why? Because if something goes wrong and your function calls itself recursively, then your whole system will hang, correct? Because every time you call yourself, you use up memory. Okay, so there will come a point of time where you don't have any more memory and the whole system crashes. All right, so that is why recursion is, though it can be very elegant, it can also be quite catastrophic, okay, if you do not handle it correctly. Okay, so this same approach, okay, let's try to look at it from the recursive point of view. So let's call it reverse recursive. Okay, so everything is going to be the same. All right, only thing is if left is smaller than right, I do the swap. Okay, so the swap is do this. Okay, so I do the swap. So I do the swap, but after I do the swap, instead of manually calling the of doing it in a loop, okay, so this recursive function basically have 3 inputs. Okay, the same, we call it using the array, the left index and the right index. Okay, and what I do is I call myself again reverse recursive with the same array, but now I say left plus 1 and right minus 1. Okay, so basically what is happening, okay, so I'm do the swap here, but after I do the swap here, I call myself recursively. That means I call myself again. Okay, but when I call myself again, I actually pass myself a smaller array. Why? Because the left index is updated to point to 1 more to the plus 1, and the right index is minus 1. So I'm actually calling myself with a smaller array each time. Okay, so the very first time that I call is this whole array. The second time will be this array, and so on. Okay, until a point of time where the left is no longer smaller than right. Okay, then I exit. Okay, so that is basically the recursive approach. That means in each iteration or each call of the function, you only do one swap and then you call again and next swap and so on. Okay, so that is basically how the recursive function can be written. All right, so in some cases it is good, some cases it is not really much of a difference. Okay, again depending on what you're trying to achieve. Okay, so of course in the sometimes they say you can have a handler function. So the idea of handler function is another function calls this recursive function, okay, at the very first time. So you can always say, for example, reverse array as a first starting point where you pass in the array Okay, and then you pass in the size. Okay, and inside this you call the reverse recursive function. Okay, where you pass in the initial index. Okay, so yeah, my handwriting is not so neat. Okay, but when I pass you the solution, you can sort of look at it. All right, so the whole idea is you at the very first instance you call this with the original array and the size of the array, and this will call this function. So when this reverse recursive function call, you will be sort of recursively calling this function until the swap is or the reversal is complete. So when you come back, okay, the array is already reversed. All right. So again, this is just you just treat it as a sort of recap or review of C programming and some of these techniques. Okay. Again, the only reason why we introduce C programming again is just because we just want to make sure that the relationship between the C and assembly, you look at it, you sort of are able to relate to it a bit better. Okay, so the last question for tutorial is this on pointers. All right. So again, pointers are always one of the key, I would say, reasons why C is still one of the most preferred languages for many low-level applications. Okay, because of the ability to directly point to memory locations and manipulate hardware. All right, so that power of C is still very strong. Okay, so let's look at pointers. So pointers, of course, are also very, very powerful. Okay, you can have many different use cases. In this case, all are integer pointers. You can even make a character pointer point to an integer, okay, and extract out partial bytes of it and so on. So there are a lot of things that you can do with pointers, all right, which make them very powerful. Okay, so let's go ahead to explore this code over here. Okay, so let's do line by line. So the first line, okay, so you have these variables declared, and the first line says B is %A. So what is A? So A is a variable, okay, that has a value of 3 inside. And now B is a pointer that is pointing to A. So when you say B equals %A means it contains the address of A. So B is pointing to A. So in the next line, you say asterisk B equals to 5. That means whatever B is pointing to, change the value to 5. So this will become 5. All right. The next line, C is equals to asterisk B multiplied by 3. So I take whatever B is pointing to. So B is pointing to a value 5. And I take that multiplied by 3. So basically it is 5 multiplied by 3, which will be 15. And I take that and put into a variable called C. Okay, so I have a variable called C. I'll have a value of 15 inside. Okay, the next thing is D. D equals to D. So D is also a pointer. All right, so now I have another pointer called D, which is also pointing to B. Okay, so the address of A comes here. So I have two pointers pointing to the same variable. Next one, E is equals to asterisk B plus C. So what is asterisk B? Whatever B is pointing to. So B is pointing to A, and A is a value of 5. Correct? So I take value of 5, add with whatever value is in C, which is 15. You give me 20 and put that into a variable called E. So I have another variable called E with a value of 20. Okay, next one, asterisk D is equals to C plus E. So C plus E is basically 15 plus 20, which will be 35, and put it into wherever D is pointing to. So D is pointing to where? D is pointing to A. So this value will now become 35. Okay. Now the next one, F is equals to %E. So now I have another pointer F pointing to E. So the address of E is inside here. Okay. The next line says A is asterisk F plus asterisk B. So asterisk F means what is F pointing to? F is pointing to E. So E is a value of 20. Okay. And what is B? B is pointing to A, which is a value of 35. So the answer is 55. So that take the value 55 and put it into the variable A. So here we have 55. Okay, and the last step is asterisk F is equals to asterisk D minus asterisk B. So D and B are both pointing to the same variable, which is A. So 55 minus 55 will be 0. Okay, so 55 minus 55 will give me 0. So asterisk F is pointing to, is basically referencing E. So this will become 0. Okay, so this is just a question to recap the concept of pointers. Okay, so again, the whole idea of pointers is, instead of just referencing a particular variable by its variable name, you can now use another variable which will now point to the variable that you want. Okay, and of course the advantage is you can point to multiple pointers can point to the same variable. Okay, and a pointer can also change and decide to point to a different variable at different times. Okay, so it sort of gives us this advantage, okay, of referencing a variable through some other means. Okay, and it's quite powerful. Okay, like I said, even though this is just a simple example, okay, in terms of referencing and being able to pass the address is one very powerful feature. Okay, I mean, very simply put, one of the key applications I can say is the ability of a function to return more than one. Right? If you remember, in C programming, generally you always have one return variable. Okay, so as I have a function called compute. Okay, I can pass in many parameters, but I can only return one. Okay, which is at the end I say return. Okay, whatever variable that I want. Okay, but if I use pointers, I can always declare them as pointer variables. So I can have pointer here that in the main function, when I call a compute function, okay, I pass in the address of the variable. Okay, so this will point back to here. Okay, so yeah, you have a question, Calvin, is it? Calvin, you raise your hand. You have a question to ask, is it? No.
Oh, sorry, Prof. Can I ask a question instead of Calvin? Yeah. So if for the first line, right, the B equal to ampersand A, is it equivalent to B equal to asterisk A?
No. Okay, so the asterisk A, the asterisk only is applicable if you declare it as a pointer. Okay, so A is a normal variable. Okay, so A is not a pointer variable. Okay, so you can only reference A as A. But B and D and F are pointer variables. Okay, so basically when you declare a pointer variable, okay, you are using this variable to point to another variable. So when I say B is equals to ampersand A, I am putting the address of A inside B. That means now B is going to point to A. Okay, but to reference or update the actual value that is inside A, I say asterisk B. So when I say asterisk B, I'm actually directly manipulating the value inside the or the value held by the variable A. But B itself, okay, so the reason why asterisk B can manipulate A is because B is holding the address of A. Okay, if I say B is equals to ampersand C, that means B is holding the address of C, then asterisk B means I'm manipulating C.
Okay. Then how do I get the pointer of B?
So B is already a pointer.
Oh, I mean you need I mean the pointer to store the pointer, right? That means it's asterisk B lah, is it? If I
okay. Yeah, I mean pointer to store a pointer means you can have double asterisks. Okay, but that one is yeah, we're not going to cover that here.
Okay, we won't touch
yeah, we won't touch pointer. Okay, but in our case, we just need to go up to one pointer is enough. Okay, but pointer to pointer is basically one pointer referencing another pointer. Okay, but again, that one is beyond the scope of what we are covering for this.
Okay, great.
Okay, so for us, as long as you understand the concept of pointer, which is basically addressing. Okay, by using a pointer, we are using the address of where this variable is stored to directly manipulate the contents inside it. Okay, so that is the power of pointers. Okay, so the sort of addressing being used to reference variable location. Okay, so that is basically okay. So question: how A equals to 35? Okay, so A is equals to 35 is okay, so A equals 35 happen over here when asterisk D is C plus E. Because D, if you recall, D already is pointing to the same place as B. Okay, so D is also pointing to A. So when I execute this line over here, okay, when I execute this line over here, asterisk D is equals to C plus E. So the value of C, which is 15 plus 20, will give me 35. Okay, and since D is pointing to A, then the A will get updated with the value of 35.
Sorry, bro. I mean, if you were to be careless and then instead of converting it correctly from pointer to integer, and then we made a integer plus pointer, right? It will still go through, right? There won't be any error, right?
Yeah, you won't see it as a compile error.
Okay.
Okay, so that's another question. What's the difference between D equals to B and D equals to asterisk B? Okay, so in this question, okay, so here, okay, when you say D is equals to B, so B is ampersand A, so D is holding the value of ampersand A, that means the address of A. If I were to replace this with D equals to asterisk B, okay, let's say you did this by mistakes, for example, then what happened? What is asterisk B? Asterisk B is whatever B is pointing to. So at that point of time, whatever B is pointing to is actually this value 5. Correct? So what happens is, if I do it this way, then what happens is my pointer D is now going to have a value of 5. That means this is the address I'm pointing to. Okay, so when I subsequently use asterisk D, I'm actually going to point to a memory location, which is memory location 5, and manipulate the data inside the memory location 5. Okay, so again, these are things that will still compile, right? The compiler will not flag off as error. Okay, but again, yeah, you have to be very careful when dealing with pointers, because again, if you make a mistake, okay, your compiler will not flag it off. Okay, only runtime errors and debugging will sort of help you figure out what went wrong. Okay, so yeah, so that sort of wraps up this tutorial. Again, this is just to recap some of the things we talked about, the number systems plus the C programming. Okay, so I think it's a good time we can go for a break. If you still have questions, you can just put it in the chat. Okay, after the break, I will address it. So we can take about a 15 minutes break. Okay, now it's 7:40. So I think 7:55 we come back. Okay, and then we will start the next chapter on the MIPS. Okay, so I'll see you all back here in 15 minutes. If you still have questions, you just put it in the chat. Okay, later I will address them. Okay, I'll see you all back here in a while. Thank you. Okay, so welcome back. And okay, so there's a question here on whether you have to be very conversant in coding. All right. So for this module, you don't really need extensive coding. Okay, so the C programming, like I said, is just to recap some concepts so that when we relate it back to the MIPS, we will need it. For the second half also, it is C programming based. Okay, but like I said earlier before, it's not like you need to figure out some complex algorithm or some technique to program or whatever. It is normal C programming. That means as long as the basic stuff like variables, loops, functions, all of those stuff you understand and you know how to do that, then I think you are fine. Okay, so as long as basic C programming you're comfortable, then you should not have any issues in handling the coding part of the module. Okay, so let's move on to the next chapter, on lecture 5. Okay, so let's okay, so what we're going to basically cover now is more instructions, okay, to understand how the assembly language sort of approach is used, okay, to carry out all the instructions that we want. Okay, so we are going to go a bit more into looking at memory instructions, okay, how we actually deal with memory. So until now, we look at some basic instructions where we said that the data is in the registers and then we just manipulate the data. Now we're going to look into some memory instructions as well, and arrays and decisions, okay, how we do branching, jumping, and so on, and some loops. Okay, so let's look at memory in general. Okay, so memory is basically a simple way to put it is just a large single dimension array of memory locations. All right, so each memory location has some data. All right, and you can just think of it as a continuous array, all right, where information is stored. All right, now each location of the memory, of course, has an address. Okay, like just now we talk about the address of a variable. Okay, when we're talking about the pointers, so every memory location is associated with an address, and the number of address locations is again related to how many bits is the address bus. Okay, so the size of the bus, all right, whether it's address bus or data bus, sort of implies the total number of locations we have to address or to access this information. All right, so in terms of addressing, there are different types of addressing. One of it is called byte addressing. Okay, in byte addressing, basically every address is corresponding to a single byte of data. Okay, like what you see here. So address 0, address 1, address 5, whatever. Each of these addresses correspond to a single byte of data. So we call it byte addressing. Okay. In terms of MIPS, generally we deal with what we call word addressing. All right. So in word addressing, what we say is the transfer of data, okay, between the processor and the memory is usually in word size. Okay, so the word size, again, it is not a very consistent term. Okay, it sort of relates back to the hardware that we are dealing with. Okay, and some processors may say just 2 bytes, 16 bits is already a word. For some, it is 4 bytes, 32 bits. Okay, some will be 8 bytes, 64 bits, and so on. So it's sort of dependent on the architecture and the processor we're dealing with. Okay, normally what we will say is that the word size coincides with the register size. Okay, and why this is important is every time I do one memory access, I can take the information and just immediately put it into that register and then start with the next step and so on. So if my register size is 32 bits, then I would immediately want to design the system such that the word size is also 32 bits. So every time I transfer data, from the memory to my processor to update the register, I can do it in one access. All right. Okay. Now, another thing is, of course, alignment of words. Okay. So in our module, we will stick to the convention that one word, okay, is equivalent to 4 bytes. Okay, one word is 4 bytes. Okay, so it's 32 bits. Okay, so that is the convention that we will stick to since we are dealing with the MIPS processor. And these 4 bytes also have to be aligned. All right. So when we say align means what? That means it always starts from byte 0 to byte 3, byte 4 to byte 7. Okay. So generally all the access is what we call aligned access, but the processor does allow misaligned access. Okay, but again, we will not go into that. Okay, so misaligned access means instead of starting from byte 0, you start from byte 1 or byte 2. So what happens is the access actually cuts across 2 words. Okay, so you can think of this as word 0 and word 1. So when the access is aligned to the addressing, okay, where you start from 0, then everything falls in place nicely. Okay, but if you try to do it across any other byte number, then what happens is the access is across 2 different words. Okay, so though it is still possible, okay, but we will consider that as a misaligned access, which we will not look at. Okay, so of course, how do we quickly check whether a given address is word aligned or not? Simply put, you just need to look at the actual binary value to relate to it. Okay, so if you look at all of this, okay, in terms of binary, okay, so 0 is 0, 0, 0, 0. This is 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, and 0, 1, 1, 1. Then you start again at 8 is 1, 0, 0, 0, and so on. Okay, now if you notice, whenever I say it is word aligned access, the lower 2 bits will always be 0. Okay, so by checking the lower 2 bits, okay, and confirming that they are 0, we can immediately say that it is a word aligned memory address. That means if I say read from byte 0, okay, read from byte 4, okay, then you automatically know that it is a word aligned access because the last 2 bits are 0. Okay, so that is how you can quickly do a check. Okay, now in terms of the registers, okay, that we know that we have 32 registers. All right, so with 32 registers, each register is 32 bits. Okay, in terms of the memory access, okay, MIPS uses what we call byte addressing. Okay, that means each individual byte has its own address. So in terms of word access, we say that the addresses differ by 4. Okay, so what do I mean by that? So I think this is a good example to tell you. So if I look at this memory, okay, you can see that every address actually increment by 1, 8000, 8001, 8002, 8003, and so on. Okay, so that is why we call it byte addressing. Okay, but at the same time, we always do word access. All right, because our registers are 32 bits, so we want to deal with 32 bits at a time. So that means that whenever I deal with one word, I'm dealing with 4 memory locations. Okay, so whenever I deal with consecutive words, so this is one word, this is the next word, and so on, the addressing is actually incrementing by 4. So you can see that this starting point is 8000. Okay, the next word is 8004, and so on. Okay, so that is what we mean by this statement here that says that the consecutive words differ by 4. Okay, because we take it as byte addressing. Alright, so every byte has its own address. So when I want to read a particular word or access a particular word, okay, consecutively, then it is differing by 4. Okay, because it's 4 bytes. Okay, so with that understanding, let's look at the instructions we have to deal with memory access. Okay, so here we have the first instruction, which is what we call the load word. Okay, so with the load word, what we have is we have 3 parts to it. All right. So the first part here is the source register. This is the destination register. And this is the offset. Okay, so how does this instruction work? So when I execute this instruction, load word T04S0, what happens is the processor will take the value in S0 register as what we call the base pointer. Okay, so what it will do is, if the value inside my S0 register is this value 8000, it will now take that is the base value of my address that I want to point to. Okay, subsequently I'm going to add an offset to it. In this case it is 4. All right, so what I will do is I will take the value in my base register S0, add with the offset to give me the final address that I want to point to. All right, so when you say load word, okay, the whole idea of load word is I want to take some data from the memory and I want to transfer it to an internal register. That is what the load word is. Taking the information from the memory and putting it into my register. So in order for me to do that, I need to know which memory I'm talking about and which register I'm talking about. So to know which memory I'm referring to, I must point to the correct memory location. So the correct memory location is obtained by performing this addition of the base address with the offset. Okay, so that is what we're doing here. So this is the base address. Okay, and this is the offset. So I take the value in S0, add with 4. So in this example, my value in S0 is 8000. I add 4, I'll get 8004. That means this is the address that I want to access. Okay, so when I access this address, I'm taking that word, which is a 4 byte value. Okay, taking this information and storing it into my destination register. In this case, it is T0. Okay, so whatever is the data over here will now be transferred over here. Okay, so that is what we how the load word instruction works. Okay, so there are 3 parts: the destination, the offset, and the source. So the source is referring to the base address. I add it with the offset. That gives me the final address of where of the memory location I want to access. So I go to that location, take that data and put it into my destination register. So that is my load word. Store word is the opposite. So store word, what am I doing? I'm doing the opposite. That means I'm taking some information in my register and updating a memory location. So it's the same thing. I need to know where is the memory location. Okay, where is the register that where it is holding the information, and from there I transfer it to the final address. So how do I get the final address? The same thing. I take the base plus the offset. Okay, so in this example, S0 is pointing is holding a value of 8000 and the offset is 12. So the offset is always, okay, if you remember, offset is always the number of bytes offset. Okay, and the number of bytes is actually, okay, this divided by 3 will give me the number, sorry, divided by 4 will give me the number of words. Okay, why? Because 4 bytes is 1 word. So when I say offset is 12, that means it's 12 divided by 4. That means it's 3 words. Okay, why? Because at address 8000, okay, from address 8000, okay, to 8003 will be my word 0. Okay, 8004 to 8007 will be my word 1. Okay, 8008 to 8011 will be my word 2. And then 8000 and, sorry, 8011. 8012 to 8015 will be my third word. Okay, so in this case, you can see that is the third third word from the base address. Okay, so every word is 4 bytes. Okay, so when I say offset of 12 means it is the third word from the base address. All right, and that is basically the address that I want to write to, because it is a store word instruction, and I want to take the data which is in the T0 register, whatever data is here, and transfer it to that location. All right, so load word and store word are basically the two main instructions you will use to perform transfer between memory and the internal register. Okay, so how do we relate that, okay, to a C code, for example? So in this C code, okay, what you have is, you say that you have an array A, okay, and you want to access the 10th element in the array. Okay, you want to access the 10th element in the array, add it with another variable H, and put the result in another location in the array, which is the 7th index. Okay, now, of course, to make our life easier, we sort of assume that there is already some allocation of registers to the variables. Okay, by right, we do not control this. Okay, in a high level language, when you click on the compile button, okay, the compiler decides which registers to use, okay, for the variables, the array, the pointer, and everything. Okay, but for our case, we will assume that some registers are already allocated, so we will say that S3 contains the base address. Okay, so when you say the base address, that means it's the starting point. So in this case, the first element. Okay, and the variable H is already stored in another variable called S2. Okay, so if I look at the first instruction over here, what am I doing? So this is the base address. So this is A0, the address of A0, plus with 40. Why 40? Because I'm talking about the 10th element. So it is 10 times 4. Okay, so again, the offset is always in terms of the number of bytes. So it's 40 bytes away. So I want to go to this array A and go in and take the 10th element and put it into my T0 register. So I take this information, put it into my T0 register. Okay, so that is the first step. Then the second step is I add T0 with S2. What is S2? S2 is the H. So I take T0 plus S2. Okay, so that will give me the answer, and I'm going to take the result and put it back into T0. All right, so that gives me this, the answer. Okay, finally, I need to write it back to A7, correct? So 7 is 4 times 7, which is 28. All right, so S3 is still pointing here. So S3 is still pointing to the base address of the register, base address of the array. So from S3, 28 bytes away is A7. So I take this answer now and I put it back into this memory location here. All right. So again, why must we do this 3-step? Because, okay, all our arithmetic and logical operations in the MIPS processor only works for registers. Okay, you do not have instructions that directly operate on memory. So if I want to do any form of arithmetic or logical operation, I need to transfer that data from the memory to my internal register first. Okay, so there's always this load word, which is the first step. Okay, because I want to transfer the data to my internal register. Then I perform the computation, and finally I write it back to the destination memory location. Okay, so that is why you always have this load word and store word, okay, at the beginning and the end. Okay, so again, besides load word and store word, you also have load byte and store byte. Again, this is for byte level access. All right, but I will not go into this so much because I think it is again not something that usually happens. All right, but it's just to let you know. And the other one is the unaligned word that I mentioned just now. That means you do not do the access across on the start of a word boundary, you do it in between. Okay, so again, these are just for information only. All right, as long as you understand the load word and store word, that is good enough. All right, these other variations is just for information that they are there. Okay, to handle this kind of corner cases where things like this happen. Okay, so let's look at this array example. So this is again similar to what we did just now, where you perform this translation, where array A is here. So the base address of array A is already in a register S3. So S3 is pointing to the starting point over here, the A0. Okay, so A1 means it is the index 1, so it is the next element, correct, which is 4 bytes away. Okay, so 1 times 4. Okay, so that's why I get 4. All right, so I want to take that value, add with a variable h. So in this case, h is in S2. Do the addition, put the answer back inside here, and finally I store it into A3. So 3 is the third index 3, so it's 3 times 4, so you get 12. Then you store it back. Okay, so that is sort of relating how you can translate the C line to the 3 assembly language lines over here. Okay, so again, one of the important concepts that you must understand is registers do not have types. Okay, so compared to your variables that you declare in your code. Okay, so in your code, you may declare it as integer x, whatever. All right, so whatever variable data type you declare, that is in your code. But once it comes to the registers, there is no differentiation. It just treats it as ones and zeros. Okay, so again, it comes back to the topic, the first topic that we did on number systems, where the computer sees it as just ones and zeros. Okay, it is the interpretation of the code, okay, and the logic behind it that gives it some meaning. Okay, whether we are treating it as integer IEEE floating point, or is it some other bitwise representation. Okay, so it is the way we interpret the value. Okay, so again, it comes down to the instruction that is also used together with this data. Okay, so this is a good example. So if I look at this instruction here, add T2, T1, T0, what can we say? We can say that we are performing an addition. So for this addition, T0 has some value, T1 has some value. Okay, we do the addition and we take the result and put into T2. Okay, so when we do this addition, we are treating T2 as a register that is holding some value, some data, and we are doing the addition operation to get a new answer. But the same T2 register, okay, if I use it in this instruction here, it is now taking the value that is in T0, adding with 0, okay, that means 0 offset, and then using this information to point to a memory location. Okay, that means when I execute this instruction, I must make sure that before this instruction, T0 already contains the address that I want to reference, the memory address that I want to reference. Okay, so the interpretation is again tied to the context, the coding that we do, the instructions that is being executed. Okay, so it is always in the context of what we are trying to do. Okay, because T0 could hold the same value for the add instruction and the load word instruction. But when I use it in the add instruction, I just perform the add operation, I get a new answer, I put it in another register. But when in the same T0 register, if I use it as a load word instruction, I am now using it to point to a memory location. Okay, so it's always in the context of what we are doing at that time. Okay, so another important thing is the addressing. Okay, so when we talk about word access, okay, word addressing allows us to increment by 1, but byte addressing increments by 4. Okay, so again, this sort of relates back to this example on the array. So if you look back at all this array example, when we talk about word addressing, we are talking about this number. Word 0, word 1, word 2, and word 3, and so on. Okay, but in terms of the byte addressing is always in multiples of 4. Okay, it's always +4, +8, +12, and so on. Okay, so these are the things that again we must be familiar and comfortable with. Okay, so let's look at another example. Okay, so one thing to note is when we are giving you some of these examples, we do not, it is not to say that this is exactly how the compiler will work. Okay, every compiler has its own set of logic, okay, to interpret your C code or high level code to assembly language. Okay, so what we are showing here is just one possible way in which the compiler may work. Okay, it can again always do it differently. It may be optimized to even compress the code even further and so on. Okay, so in this case, we are doing a simple swap example. So if you remember, swap basically you like what we did just now for the reverse array. All right, we are trying to swap the elements. So how can the swap work in a simple assembly language code? All right, so let's look at this example to understand what is happening. Okay, so we want to do we have this array V, and we want to swap basically the element that is indexed by K with the next element, which is K plus 1. Okay, so if K is 3, that means I want to swap the data in the index 3 with index 4. Okay, so that is basically what this code is trying to do. Okay, you are doing a swap, but the swap is always with whatever index we specify with the next element. Okay, so we have already given you some variable mappings here. Okay, so K is in register 5, base address of V is in register 4, and the temp variable is in register 15. Okay, and we are also given this assumption the base address of V is 2000. So what is happening here? Okay, so let's look at it line by line. So we know that the value of 3 is inside register 5. Okay, and the value of 2000 is inside register 4. All right, so that's the first thing. So we have two registers, we already know the value. Okay, so register 4 having a value of 2000. Okay, and register 5 having a value of 3. Now this first instruction over here, SLL 25, okay, register 2, register 5, and value 2. Now SLL, can you all remember what is SLL? We did it in the last lecture. Anybody recall what is SLL? Okay, so if you can't remember, you can just refer back. Okay, it's basically shift left logical. Okay, shift left logical. So for this shift left logical, basically, if you remember, okay, let me show you back, show you the thing we discussed last lesson. So for shift left logical, if you remember, whenever we shift left by 1 is equivalent to multiply by 2. Okay, when you shift right by 1 is equivalent to divide by 2. All right, so that is basically how the shift left actually helps us. Okay, so what is this code doing here? Okay, so you can see over here that I'm taking the value which is in register 5 and I'm doing a shift left by 2. So what is inside register 5? It is the number 3. So I'm taking 3 and I shift left by 2. What happens? Okay, whenever I shift left by 1 is equivalent to multiply by 2. If I shift left by 2 is equivalent to multiply by 4. So this is equivalent to saying it is 3 times 4, which is 12. Okay, so the value of 12 goes inside register 2. Okay, so again, why shift left by 2? Shift left by 2 is equivalent to multiply by 4. And why multiply by 4? Because we always have to translate the byte addressing to the word that we want to access. Okay, so since we want to access the word, okay, which is index 3, it is actually 12 bytes away. So I'm going to do a 3 times 4. Okay, so to do the 3 times 4, I do a shift left by 2. Okay, so that is why we have this SLL. Now the next one, add operation. So add operation, what is happening? I'm taking 4, add with 2, and putting into 2. Now what is 4? What is 2? Add register 4 as a value of 2000, which is the base address of B. Okay, so now register 4 as a base address, which is 2000, add with what is in register 2. So what is in register 2 is 12. So here what I'm doing is I'm taking 2000 plus 12, which is 2012, and putting it back into register 2. Okay, I'm putting it back into register 2. So right now I have another register 2 that is having the value of 2012, which is actually the address that I'm interested in. Correct? Why am I interested in this address? Because I want to swap V3 with V4, and V3 is 2012. Okay, so before I go to the other line, so far, do you have any questions or anything that is not clear? Anybody wants to ask anything to clarify first? Okay, so question, how to get 12? So the 12 is because this first line here, which is the value of whatever is in register 5, shift left by 2. So what is inside register 5? Inside register 5 is the value of variable k. So in this example, the k is 3. So 3 shift left by 2 is, again, whenever you shift left by 1, okay, so maybe I show you here. So if I take the value 3, is 0, 0, 1, 1. Okay, if I do a shift left by 1, what will happen? It will become 0, 0, sorry, 0, 1, 1, 0. Correct? If I do one more shift left, what will happen? It will become 1, 1, 0, 0. And what is this value? This is 12. What is this value? This is 6. Okay, so 3 shift left by 2 is equivalent to 3 multiplied by 4. Where every time I shift left by 1 is by multiply by 2. So total is multiplied by 4. Okay, so generally it is normal to feel a bit lost and confused in the initial stages, all right, because again, this is not something that most of you may not have exposure to before, all right. I mean, you may have done a lot of high level programming, all right, but again, at the low level, I think this is probably the first introduction to for many of you. Okay, so it is quite normal, okay, to feel a bit unsure or a bit lost of what is happening. Okay, so don't be concerned, so you're not the only one. All right, even all the full-time students also go through the same thing. All right, the very first time they look at all this assembly language code, it's a bit overwhelming. All right, trying to relate registers with values and memory and address and all this stuff. Okay, so it takes some initial it takes some time, okay, to get through the initial barrier of trying to put things together. Okay, but I can show you that once you sort of go through the slides again, and try to figure out step by step, then you realize, okay, it falls in place and it's easy to follow. Okay, but it does take a bit of while to get used to it. All right, so in this first line, basically what you're doing is we are taking the value of 3 shift left by 2, which is equivalent to multiply by 4, so you get 12. All right, in the next instruction I'm doing an add, so I'm adding the value in register 4, which is 2000, with the value in register 2, which is 12, and that will give me 2012. And why do I want 2012? Because this array B, okay, I'm interested in the element 3, index 3, okay, which is from the base address offset of 12. Okay, now let's look at the next instruction here, next two instructions. Okay, so in this instruction here, what am I doing? I'm taking the, okay, so firstly we know load word. Load word means I want to take from the memory and put to my register. So there's two things. Firstly, which register and which memory location. The register is of course quite easy to see, is register 15. Okay, so this is the register that's going to hold the data for me. Now the next question is, where am I taking the data from? Okay, so where am I taking the data from is from this. Okay, so from what we just saw, this is actually two parts. The register 2 is the base address and this number is the offset. So what does register 2 contain? Register 2 contains the value 2012. That means I'm already pointing, so register 2 contains the address that is pointing to the index 3 element, okay, at address 2012. So I'm going to take this data, okay, and put it into register 15. Okay, so that is what the third line is doing. I'm taking the data that is inside memory address 2012 and putting it into my register 15. Okay, and this address 2012 is basically what is referenced as B3. Okay, now the next step is, let's look at the next instruction here, the fourth line over here. Again, the same thing, it's the load word instruction, but in this load word instruction, we are taking the register 2 plus offset of 4 put into register 16. Okay, so register 2 is pointing to index 3. So if I take register 2 add, okay, if I take register 2 add with the offset of 4, I'm actually going to point to index of 4. So I'm now going to point here now. Okay, because register 2 is pointing to index 3. Okay, if I add 4 bytes, where the value of 4 is going to point to the next index, which is index 4. So I'm going to take this content and put into register 16. All right. So that is the first step that I'm doing here, or the first 4 lines of code that is being done here. Okay, I calculate the offset. I add the offset to my base address. So I'm now pointing to the new address, and then I take the data from there and the next data and put it into two registers 15 and 16. Then what I'm doing is I am doing a store from 16 to 20. So what am I doing here? Store word is the opposite, correct? That means I'm taking the content of my register and putting it into the memory location. So the content inside register 16 is what? Okay, this is from the index 4. This is from the index 4. Okay, so I should put it this way, index 4. And I'm putting it into 2 plus 0. So register 2 is actually pointing to index 3. Okay, so I'm taking this data over here and now writing it to this location. Okay, so that is what is happening here. Okay, and then in the last line, I'm taking the content of 2 plus, taking the content of register 15, which is actually the original register index 3 content, and putting it into register 2 plus 4. Register 2 plus 4 is currently pointing to the 4th element in the array. This one will now point to here. All right, so basically, okay, what we're trying to do is we're going to take, okay, from 15 and 16. So we're going to take from the S2 register plus 4 bytes offset from it, okay, which is basically this over here, K and K plus 1. That means the index and the next index. Okay, I do a swap, okay, by storing it in the appropriate locations after I take it from the memory. All right, so again, if you're still not very sure, it just takes some time. Okay, you probably need to go through again line by line to sort of understand what's happening. Okay, so let me just run through this one more time. Okay, just to be sure. Okay, so I just want to be sure that you have all of this clear. Okay. Okay, so let me just go through this again one more time, just to be sure that you understand. Okay, so what we have here is this C statement, and basically what we do is we want to do a swap. Okay, so here we have a variable v, okay, which is a base address of an array. So this is v0, v1, v2, v3, v4, and so on. Okay, so what we are saying here is, if I call this code with a particular index, let's say k is equals to 3, then whatever is in 3 and 4 must swap, must exchange, the content must exchange. So that's why it is k and k plus 1. Okay, so that is the objective of the C code. At the same time, we know that the base address of the thing is 2000. Okay, so 2000 is the base address of the array B. All right, and this is stored inside the variable 4, register 4, sorry, register 4 is having a value of 2000. Okay, the K, which is the index, is stored in another variable, we stored in another register 5. Okay, so in our example, we are saying the value is 3. Okay, so in the first line, okay, in the first line over here, what we are doing is we are saying shift left logical the value in 5 by 2. Okay, so as we saw just now, whenever I shift left by 2, it is the same as saying multiply by 4. Okay, so again, why multiply by 4? Because the indexing is just going in sequence. Okay, but in terms of the bytes, each location is 4 bytes, so you need to multiply by 4. So 3 multiplied by 4, okay, so this is value 3 multiplied by 4, I'll get a value of 12 into register 2. Okay, so register 2 is now going to have a value of 12, which is the number of bytes of offset. Okay, now the next thing is I add the register 2 with the register 4. So what is happening? Register 4 is the base address and register 2 is the total number of offset of bytes. So 2000 plus 12 will give me 2012 and I put it back into register 2. Okay, so now register 2, okay, has a value of 2012. Okay, then what am I doing? I am going to load from the memory location, which is address, which is pointed to by register 2 with the offset of 0. So register 2 is pointing to or having the value 2012 and the offset is 0. That means there's no offset. So I'm pointing to this location here. Okay, I want to take this data and store it into register 15. So this content is going to come into register 15. Okay, so let's just put in some value. So maybe I'll just say that the value inside here is 25. So the value 25 will come here. Okay, now in the next slide, what am I doing over here? I'm doing the same thing, but this time around, I'm taking the content of based on the base address of register 2 with offset of 4. So register 2 is pointing to address 2012 plus 4 will be 2016. So I'm pointing to the next memory location, which is this. Okay, and I'm going to take that data and I'm going to put it into register 16. Okay, register 16. So let's put this as maybe value 88. So this value 88 comes here. Okay, so that is the to load word instruction, and then I'm going to do a store word. So in this store word, what I'm going to do, I'm going to take the content in register 16 and put into the location pointed by register 2 with 0 offset. So register 2 is still pointing to address location 2012, which is B3. So I'm going to take this and I'm going to put it inside here. So what will happen? Instead of having a value of 25, this will now have a value of 88. Okay, and then in the last line over here, I'm going to take the value in register 15 and put into which location? The location pointed to by register 2 with the offset of 4. Register 2 is pointing to 2012, which is index 3, plus 4 is 2016, which is index 4. So I'm going to take this value and put it inside here. So this will become 25. Okay, so that is basically what is happening. So in the C code, of course, it's very easy to relate. Okay, because we can see that, okay, I just move variables around. Okay, create a temp variable, move things around. Okay, but in this example, you can see that the translation of the C to assembly is not one-to-one. Okay, we did not do, I mean, it is somewhat one-to-one. Only thing is, it is not so straightforward as what you see in the C code. Okay, it's not so straightforward. So that is where the understanding of the instructions and interpreting this load word and store word all comes in. Okay, so I hope, okay, those of you who had some doubts, maybe it's a bit clearer now. Okay, after I explain again. All right, if you're still not sure, or things are still not clear, okay, then it's just a matter of maybe going through one more time, okay, when you're free, and trying to look at it step by step, okay, and then you should be able to get it. Okay, so let me come back to our slides here. Okay, so those were the memory access instructions. Okay, now the next thing we're going to look at is making decisions. So of course, making decisions is like how we do if else and go to or switch case statements. Okay, in your high level language. Okay, so let's look at it from the perspective of the assembly language. So in assembly language, you have two common branch instructions called BNE and BEQ. So BNE means branch if not equal, BEQ means branch if equal. Okay, so if two registers have the same value, then we will then we can say that branch is equal. If they're not the same, then you can say branch is not equal. So it all depends on what kind of a check we are doing. So in this case, when we say branch means, okay, instead of executing in sequence. So until now, when we look at the example code, everything, we are going in sequence, correct? Okay, so the branch, basically what it does, it allows us to skip some lines of code and go somewhere else. Okay, so for example, I have some lines of code, and then I have a code here that says branch if equal T0, T1 with label. Okay, so let's say this label is somewhere here. That means if I decide to take the branch, then okay, all this line of code will be skipped. Okay, so I will straight away jump. Okay, if the condition is true, that means if T0 and T1 are true. Okay, so a label is just what we call an anchor. That means you just take some line of your code and give it a name. Okay, so labels are not instructions, they're just a name given to a particular line of code, so that you can say that this is a particular place that I will jump, I will be able to go to, okay, if some condition occurs. Okay, so besides branch, you also have a jump instruction. Jump is what we call unconditional. That means you do not depend on any condition, whether it's equal or not equal, or whatever. You straight away just jump. Okay, so if I execute this instruction, I will just jump to wherever it is, wherever you have the label in your code. All right, so the two again, branch is equal and branch is not equal. So in terms of C, it is easy to relate to. If A equal B, then I go to a particular line, L1. If A not equals to B, then I go to this line L1. Okay, so that is the sort of translation from C to assembly. Okay, in terms of jump, again, it is equivalent to saying like a go-to instruction. Okay, go-to instruction. Okay, so let's look at if statements, okay, and see how they can be translated to C code using the branch instructions. Okay, so what we have in C here is we are doing a check. Okay, if I equal to J, that means if these two variables are the same, then I do this. Okay, how can we translate this to assembly language? So one way, so we are looking at two possible ways. All right, and this is the interesting part. Okay, sometimes doing a direct translation may not be so efficient, but if you think of it from the reverse perspective, you may have more efficient code. Okay, so what do we mean by direct and reverse? So let's look at the first one over here. So in this first line is the direct translation. Why I say direct? Because in C it is comparing whether they are equal. So here also we are saying comparing if they are equal. So if S3 and S4 are equal, then I jump to a particular, I branch to a particular line L1 where I perform this execution of the addition. Okay, so what happens if it is not equal? If it is not equal, then I won't take the branch. So I will go to the next line of code. And the next line of code must be an instruction that skips the add operation. Okay, because the add operation here must only be carried out if the condition is true. Okay, but if the condition is not true, then I'm supposed to skip the add operation. So I have another instruction here that says jump to exit. So I go to the line after the add instruction. Okay, so that is what the direct translation is. Okay, so logically it is correct. Okay, logically it's correct, it works. Okay, but it is not so efficient. Okay, because you have a branch plus you have another jump. Okay, but if we reverse the thinking, okay, by using this thing called branch if not equal. So if it is not equal, I come to the exit. That means if it is equal, that means if S3 is equal to S4, then I will actually execute this line, which is what we want, correct? If the condition is they are equal, I will execute the addition. So I will only branch if they are not equal. If it's equal, I will execute the add operation and I will immediately go on to the next line and so on. All right, so you can see that this reverse thinking, okay, actually can produce a bit more efficient code. Okay, so you don't have unnecessary jump instructions there. All right, but you can still implement it based on the logic that you want. Okay, let's look at another example. See if double equal. Okay, so in this example here, we are trying to check whether I equal to j. Then if it's equal, you do addition. If it's else, you do a subtraction. Okay, so again, C is very easy. The flowchart also is very straightforward. Okay, in terms of the code, let's see what happens. So in this case, branch if not equal. So if it's not equal, I come to the else. So this is the else condition. So this is the not equal. So if it's not equal, what must I do? I must do the subtraction operation, which is what we do here. Now, if it is equal, then of course I will not take the branch. So this is the equal case. So it's equal, I will do the addition. If it's not equal, I'll do the subtraction. Okay, but you notice that after I do the case for the equal, I must have a jump to skip the line that does the subtraction. If I don't put this jump, what happens? Okay, I will execute the first line. Okay, for equal case, I will execute the add and I'll also do the subtract. Okay, I'll also do the subtract because in assembly language, everything is just like in C, everything is sequential. So I execute the first line, the second line, and third line, and so on. So the B and E, okay, so if I do not take the branch, I will execute the add operation. If I don't put the jump, what happens? I will also go ahead and do the subtract execution. Okay, so to prevent this from happening, I need to make sure that if I do the add, I skip the subtract. So that's why I jump to the line after the subtract. Okay, after the subtract. Okay, so this sort of again gives you the idea of how to translate C to assembly. Okay, with this thing, thought process. Okay, so here is the other way where we are given you a MIPS code and ask you to translate to C. So in this case, branch if equal, S1, S2 the exit. So if not, I come here. So this line will only be executed if it is not equal. Okay, because if it's equal, I would have jumped to the exit. So only if it is not equal, I would actually come to do the add operation. So in terms of C, it is just something like this. If I not equal to J, then I assign 0 to a variable F. Okay, so that is one example. All right. Now let's look at the loops. Okay, so in terms of loops, all right, how can we translate? So here I have a loop that says that while J equal to K, I keep incrementing I. Okay, in terms of translating it, you can use what we call go to. All right, so basically, when you look at loops in assembly, you just need to have a right combination of go to statements with some branch statements. All right, so you can rewrite the loop with if and go to statements, and once you have if and go to statements, you can easily translate that to MIPS. Okay, when you look at it from the higher level, it's a bit more difficult to translate to MIPS. But if I translate it into a go-to statement sequence, so if J not equals to K, I go to exit. If I equals I plus 1, go to loop. I mean, after I plus 1, go to loop, and so on. All right. So in normal C programming, we definitely discourage such things. Okay, because you do not want your C program to have all these labels and all over the place. Okay, but when you want to relate it to assembly, rewriting it this way actually helps. Okay, so in terms of translating it to MIPS, you can see that if J not equals to K, go to exit. So branch is not equal. So if not equal, go to exit. Okay, which is this. So this line will be executed if J equals to K. Okay, so if J equals to K, what do? I just increment my variable I and then repeat the loop. So I increment and jump to loop. So come back here. Okay, so this is another example of a for loop. All right, so here what you can do here is you first initialize I. So how do you initialize? How do I assign a value of 0 to a variable? I add 0 with 0, put into the destination. Okay, so this first line, what does it do? It takes the value 0 and 0 put into S0 register. So after that, S0 will be having a value of 0. And our mapping says that S0 is I. Next, I want to have the variable 10 also stored in the register because that is my exit condition. Okay, so I add immediate 0 with 10. So 0 add with 10 is 10, put into register S1. Okay, so S1 having as a value of 10. Okay, and I want to repeat this loop right from 0 to 9. So the moment I hit 10, I must exit. So that is where the first line. So if I equal to 10 is exit. Okay, so until then, so y is lesser than 10, I will still run the loop. So when I run the loop, what do? I increment the variable I with the value 5. Okay, so to increment the variable I a with the value 5, I take the variable a map to S2, do an add I. Add I is, again, look back at the last week lecture, if you forgot, is add immediate. So there's two types, add and add I. So when I just take add, it is 3 registers involved, 2 source register and 1 destination register. If I take add I, it is 1 source register plus 1 immediate value and put the result in another destination register. Okay, so A equals to A plus 5 is here, and then I add I equals to I plus plus is here. And then I jump back to the loop and so on. Okay, so of course, in our C code, generally we also have less than, greater than, and so on, correct? Okay, so how do we relate that? So that is actually a bit more complicated because there is no real BLT. There is a pseudo instruction, okay, which we will discuss when we look at the instruction set. But basically in MIPS, what we do is we have an instruction called SLT. So instead of branch if less than, there is an instruction that says set if less than. Okay, so this SLT instruction actually relates to this. If S1 is lesser than S2, then this register value will be set. Okay, if not, it will be clear. So there is this SLT instruction. All right, so what you can use is you can use this SLT instruction first to check whether one variable is greater than or smaller than the other, and then after that you can decide to do a branch. Okay, so if I want to do a branch with less than, what I can do is do something like this. So let's look at this and understand what is happening. SLT T0 S1 S2. So if S1 is lesser than S2, then what will happen? T0 will become 1. Okay, so if S1 lesser than S2, then T0 will become 1. Then you can say branch if, so rightfully what we want to do is if T0 equals to 1, then we can say branch to the particular location L. But again here you see that they never do a thing that BEQ T0 with 1. But I say branch if not equal T0 with 0. Okay, and this is actually the same as saying branch if equal T0 with a 1 to L. Okay, but the problem with this is that there is no comparison between a register and an immediate value. Comparison are always with register and register. So if I want to do this comparison, then I actually need to take this one and put it into another register first. So I need to have an additional instruction to load a value of 1 into a register, and then I can do a compare. Okay, so to minimize that unnecessary step, okay, what you can do is you can do the reverse thinking. So you can say a branch if not equal T0 with 0, which is equivalent to saying that branch if equal T0 is 1. All right, so again you may think that why so troublesome, why must I go through all this? Okay, why can't I just write it the way I think it should be written? Okay, so again, if you write it the way you think it should be written, it will still work. Okay, logically it will still work. Only thing is it may be requiring more steps, more instructions, and so on. So it may not be as efficient as the techniques that we are showing you here. All right, so logically it is still correct. Okay, it's just about whether one technique is more efficient than the other. Okay, so let me see where are we. Okay, so it's only about 3 more slides. So I think let me finish this, okay, and then we can call it a day. Then when we come back after the break, we start the next chapter. Okay, so this one is again quite similar to what we did just now, relating array and loop. Okay, so in array and loop, basically what we're trying to do is we are trying to always remember that we have to have the base address of the array that we're talking about. Okay, which is the element we are referencing and where do we want some result to be stored. Okay, so in this case, for example, we want to count the number of zeros in an array A. Okay, so we have an array A, okay, with a lot of different values. Okay, so maybe some is 5, 2, then maybe some of it is 0, then this is 91, okay, and so on. So we want to go through the entire array, which is 40 elements, and we want to count how many of them are 0. So for example, this is 0 and so on. Okay, so how do I write it in C? So C is of course quite straightforward. Okay, we just do a loop, do a check, and then we keep count of a variable. In terms of assembly, let's see how it can be done. So I need to first declare some variables. So in this case, I take T8 to be the result, T1 to be I, and the address of A in T0. Okay, so this two is to initialize the values. So initially the result is 0 and initially I is 0. Okay, and I also want to indicate the endpoint, which is 40. So I put T2 as 40. So T2 as a value of 40. Okay, because I have 40 elements. All right. So when T1 is greater than T2, so this is checking for what? When I is greater than 40. Okay, greater than or equal to 40, then I will end the loop. Okay, so I need to go until the 40th element. All right, and for each time I go through the value I. So you have to remember that when I look at I, this is I equals to 0, I equals to 1, I equals to 2. Okay, and if you remember just now the example, this is the index, but in terms of memory addressing, it is always multiplied by 4. So that is why I always do this shift left logical by 2. So the index shift left by 2 is the same as multiply by 4. Okay, so what is happening here is I'm taking the current index multiply by 4 and putting it into a value called a register called T3. Okay, so my register T3 is now going to point to whichever is the correct index of the array I'm accessing. Okay, and I'm going to add T3 with T0. Okay, so what is T0? T0 is the, sorry, so T3 is the offset. So originally T3 is the offset, and then T3 add with T0. So when T3 add with T0, which is the base address of the array A, and I'm going to take that and put into register T4. So these two add together, put into register T4. And T4 is now going to point to the correct location in the array A. Okay, so this is actually quite similar to just now the example we went through. Okay, which is basically we take the index, which is in this case T1. Okay, so T1 is the I. Okay, the index, and I shift left by 2, which is multiplied by 4. Okay, because it is one word at a time, it is 4 bytes. And then I add it to the base address of my array, which is T0. So T0 is the address of A0, the first element. And I add the offset to it to give me the address, the new address based on the current I value. And that is in T4. Okay, then what do? I do a load word of T4 with 0. That means if T4 is pointing to this location, I take this data and put it into register T5. Okay, and then I check whether the value is it equal to 0. So if it is not equal to 0, okay, if not equal to 0, that means I don't need to do anything. So I add T1 by 1. So this is basically I plus plus. Okay, T1 is your I. And then I go back to the beginning. Okay, so this branch to skip happens if the value is not equal to 0. Okay, but what do you want to do? You want to count how many of it is 0, correct? So if I do not do the branch, that means if I come to this line, that means the value is actually equal to 0. Correct? That means I did not take the branch. So if I did not take the branch, I'll come to this line. That means I add T8 by 1, and T8 is the result. So I keep track of how many of these elements in the array have a value of 0 inside it. All right, so that is basically what this loop is doing. Okay, now there is of course many different ways to write the code. Okay, so this is just another example where we use the concept of a pointer. All right, so in the concept of a pointer, basically what is happening is we directly manipulate the address in the variable or in the register itself. Okay, so let me tell you what we are doing here. So firstly, T8 is 0, there's the result. Okay, and then what we do is we take T0, which is the address, okay, add with 0 and put into T1. So T1, in this example, T1 is originally pointing to the first element in the array A. And T0 add with 160 put into T2. Okay, so T2 is now holding the address of the last element. Okay, so this is the last element. Okay, so why 160? Because 40 elements, correct? So 40 times 4 is 160. Okay, so it's now holding the address of the last element. Okay, so what I'm going to do is every time I access element, T1 is going to increment. And the moment if T1 is greater than or equal to T2, I will end. So what I'm doing is I'm comparing the address. Okay, so once T1 is greater than or equal to T2, that means I already reached the end of the array. So I end. Okay, if I haven't reached the end of the array, then I do what I'm supposed to do, which is take the content. So firstly, I take this first content, I put into T3. Take this and put into register T3. All right, and then if T3 is not 0, then I skip. So this is same as just now, same as just now. So I come here. So this is when the value is not equal to 0. If it's equal to 0, then I increment by 1. Okay, so what is different is this. After I come here, I'm supposed to increment the index. Okay, but now I'm not doing index counting. I'm doing direct address counting. So I straight away increment by 4. So once I finish this, I straight away increment by 4. So I point to the next element. Okay, so when I come back here, I'm pointing to the A1 and so on. Okay, so this is basically what we call the pointer version, because we are directly looking at it based on the address of the elements. So in this earlier example, we are looking at it from the indexing point of view, okay, from the array index. So I use the index and then I shift left by 4, okay, and then I add it and so on. Okay, here I don't do that because I automatically increment by 4 for every memory access. All right, so again, this is just two different ways of doing the same thing. Okay, so it sort of gives you the idea that, you know, the higher level C code could be one approach, but the lower level assembly could have different versions of it, okay, depending on the compiler and how it tries to interpret it. Okay, so that sort of gives us a wrap up of the MIPS assembly language. All right, so of course, even though it's CS2100 here, it's the same for our module. So it's 2401 is also the same. Okay, where we wanted to cover some basic examples, all right, and how it goes about. All right, so when we come back from the break, all right, after Chinese New Year break, I will talk about the first assignment, which is on this programming, MIPS assembly language programming using a simulator tool. Okay, so I will explain that and how to go about it. Okay, so it's fairly easy. All right, you just need to do some simple assembly language programming using the software. All right, and test it out and just show the results and everything like that. All right, so that is something we will discuss when we come back from the break. And after, of course, when we come back from the break, we will also start on the next part, which is on the MIPS architecture. Okay, the software is this software called Qt-Spim. Okay, don't worry, I will give all the software file downloads, everything in Luminous, so you don't need to go out to find it or anything. Okay, so I'll provide all the software in the Luminous. All right, so yeah, that's about it we have. So basically, even though MIPS itself, we sort of finish it here, we are still going to look at MIPS when we look at the processor architecture starting from next week. Sorry, next week. Okay, so before we end, just wishing you all a happy new year. All right, hopefully 2022 is much better for all of us. Okay, and we can all go back full time into our campus and our work. Okay, so there won't be any videos or makeup lessons for now. All right, we will skip next week and we'll resume the week after next. Okay, then as the weeks go by, if we need more time, then I will schedule a makeup. All right, so for now, there is no makeup. We will just skip next week and we'll resume from the week after next. Okay, so again, have a nice break, nice holidays with your family, and I'll see you all after Chinese New Year. All right, thank you.